Greetings and welcome to the introduction to astronomy. In this video, we are going to talk about the hydrogen energy levels lab and simulator. And as with others, there is a interesting amount of information here that you can look at. So there's some background information. Make sure you look at these first, because that will give you some of the important details you need to work on the simulator. But really what we want to look at here first is the hydrogen atom simulator itself. So as we pull that up, it will show a few different things. First of all, it shows the atom here on the left hand side, and we have the proton for the hydrogen atom at the center, and then the electron orbiting it, in this case in the very first or ground energy state. And there are various other energy levels: the second energy level, the third, the fourth, the fifth, and the sixth. And the electron can be present in any one of these energy levels. It will always want to be in the ground state or level 1, but it can move up into the others if properly excited. Now we can also see it as an energy level diagram here. It's highlighted to show where the electron is at this point and what the energy is of that level. So for example, if we wanted to move that electron and bring it into the second level, you can see how it's moved up here and how the energy has changed. Now, if you note, it didn't last there for very long. Atoms do not like to be in excited states, so they have a tendency to decay. The electrons will always go back down to the ground state. Now, other things we can see in the simulator here are when you're selecting the photon you want to use, you can look, and this will tell you the frequency. The second graph shows the wavelength, and the third shows the energy of that photon. And there's a slider here showing infrared, visible, and ultraviolet photons. In addition, there are some pre-programmed photons for different series of hydrogen lines. These are the Lyman series, and those are associated with transitions from the first level. So Lyman alpha is from 1 to 2. And that means if I were to click on Lyman alpha, it would take the photon. It would shoot a photon of the precise energy to bring that electron up into the second energy level. If you bring one that is the incorrect energy level, then it would not be able to, it would be unable to move that photon out. So we could pick some other random photon while this is in here. Let's try the H alpha photon right here. And if we click on that, it will tell you that nothing happens. That photon is not of sufficient energy. These are the H alpha and beta and gamma. This series here is what we call the Balmer series. And these are important because these are the ones that we see in visible light. And then there's the Passion series, which is visible in the infrared. So let's go ahead and clear those. And we can then fire different photons and try to look for the energy levels that are needed to move photons up the level. So for example, if we want to go from the first level to the second, the Lyman alpha will get us there. And then if we then want to go from the second to the third, the H alpha following right behind it could do the same thing. And now we'll watch as this decays. In this case, it didn't decay the way it went up. And you can see in the event log over here on the end, which is right here, that the excitation was done in 2 steps. In this case, it absorbed a photon of this wavelength, and then it absorbed another wavelength photon. And then the de-excitation was exactly 1. It gave off just 1 photon. But what you should notice is this one was 10.2 electron volts. And the next one was 1.89 electron volts. And if you add those up, you will get 12.09 electron volts. And what that is that's exactly the same as the photon that was emitted. So the amount of energy that was absorbed in these 2 states is equal to the one that is emitted. Now you can also get other types of de-excitation. So if we were to take our electron and drag it out to the far level here, out to the 6th level, and we can see what happens to it. And in this case, you can see it drop down a couple levels, and then it dropped all the way down. So it did this in stages. So we excited it to this further level, and it gave off 2 different photons. Now in that case, it would have given off photons well off in the infrared and then 1 in the ultraviolet, so nothing that would be visible to us. The visible light photons would be the ones that involve, again, this second energy level. And if we do the H alpha one there, again, you can see that's a red photon that it shows, and that will jump it up 1 energy level. And that would be something that is part of the visible spectrum that we are able to see. So looking at the controls here, these are what you will use to try to figure out, and you can change the photons. You can try other ones. You don't need to use just these. You can actually will have to try some others and see what happens if you send a photon of 550 nanometers in there. And if you fire that photon in of green light, absolutely nothing happens. You can experiment what might happen if you put it in this level and fire that same photon, and guess what? Still nothing. And that's because that photon is not the same, does not have the same energy as the difference between 2 of these levels. Now if you bring it up even further and fire that same photon, all of a sudden now it ionizes it. That photon had enough energy to rip the electron off altogether. And you'll see that it will eventually recombine in addition. But if you have a sufficient amount of energy, if you send a very high energy photon, even when the electron is in the ground state, if you send a high enough energy photon, it will knock that electron off. So it will not necessarily just bring it up to a higher level. In order to get it there, it has to be that precise energy. If it is anything different, if it is just slightly off, then the electron will not be able to see that photon, and it will pass right through the atom. So if it has sufficient energy, it can ionize it, take the electron off. If it has exactly the right energy, it can cause it to move between energy levels. But anything else is going to not do anything, and the electron will just sit there and will then finally decay back to the ground state. Now there is one second simulator, not a full simulator here, but one other thing that you'll look at within the level abundances, and I'll just take a minute to show you that as well. And you're going to be looking at that to make a graph of these abundances. And what this shows is the number of electrons in the first level here, the second level, the third level, the fourth level, and the fifth level, and how many have been ionized. At very low temperatures, it's a very small number of electrons that are in this level. And remember, this is the one that gives us visible light. So if we want to see the transitions with a visible light telescope, they need to start from the second level. If they're in the first level, they are ultraviolet transitions. Now, if we clear this and then we look at if we change the temperature, we can see that the distribution will change. So as we raise this temperature, you can see that all of these tend to increase, that we get more and more electrons in the higher energy levels. And then if you increase it enough, then the actual levels start to decrease again, and the ionized levels becomes the dominant. So at very high stars, most of the hydrogen is actually going to be ionized. So we will not see a whole lot in the other portions. And when we have a much cooler star, most of it is in the ground state. Now when you're graphing this, you do have to look at some of the numbers. So if we look at some here, the graph within your section is given in 10 to the 15th power range. So it's 10 to the 15th power. And if we look here, this value at 2,300 degrees is 5.25 times 10 to the 16th. So let's put that up here. 5.25 times 10 to the 16th power. So this would be when you're scaling it to 10 to the 15th, you essentially can get rid of 15 of these zeros here. So this becomes a 1, and 5.25 times 10 to the first becomes 52.5. So for the purposes of the graphs, you just want to remove 15 from this and then figure out what your number is. And that's what's going to go on your graphs. So that concludes this video looking at the hydrogen energy levels simulators. We'll be back again next time to look at another one of these simulations. So until then, have a great day, everyone, and I will see you in class.